All right, so Hichem from University of Louisville. I hope I'm saying that right. Hichem.
Yeah, close.
Welcome. Thanks for
Thank you.
joining us today. He's going to be talking about machine learning applications. So you are actually going to be sharing your screen, correct? So
Yes,
I will
yeah.
stop sharing mine and let you take control. So you could go ahead and introduce yourself, and then you're free to get started.
All right. All right. Hello, everyone. My name is Hichem Frigui. I'm a professor with the computer science at the University of Louisville here. And today I'll be talking about some of the machine learning projects that we've been doing in my lab. So I'm the director of the Multimedia Research Lab. This is within the Computer Science and Engineering Department at Speed School of Engineering. I have another faculty member with me, Dr. Andrew Karam, and we currently have 7 PhD students and 2 master's students. Been here for the past 15 years now, and my lab has graduated 17 PhD students, and all in working in one aspect of machine learning or AI. And many of these students are currently with Facebook, Microsoft, Google, and some faculty members. So our focus is mainly machine learning or AI and deep learning, and we put an extra focus on explainability. So most of the AI or deep learning methods, you give them input and they'll give you an output, and we try to focus and come up with a reason why the system made that decision. And we deal with a lot of and some of the applications that I will discuss today, they'll have different types of data. The engine is the same machine learning, the same AI algorithmic part, but the data can be text, image, audio, and video. It could be infrared images, hyperspectral images, LiDAR data, radar, and so we handle many types of data. We've been supported by several grants from the Department of Defense, several divisions, National Science Foundation, Kentucky Science Engineering Foundation, and few industry funded projects too. So I have about, I think, 6 projects. I'll be watching the time, and if I have enough time, I'll try to probably cover all of them. Otherwise, I'll stop and cover as many projects. So the first one is automatic recognition of vehicle make, model, and year. So let me go. So this is, if you're familiar with classification and learning, this is slightly different because we're not interested in telling the difference between, let's say, a car and the dog or a car and the person. We're more interested at the finer details. How can we tell the difference between different cars? For example, can we distinguish between a Honda and an Acura, or even within the same make, how can we distinguish between different models and different years? So here's kind of, so I'm avoiding all technical details here. I'm keeping it only at a very superficial level. So if you're given a car and then it goes through this network after we train, the goal is to tell me what is that car. So I have sample outputs here. So the first image there, you give it that image, it will tell you it's a Nissan Altima, and the year you have, because we cannot distinguish between the 2002 and 2006. The next one, it is a Toyota Corolla between 2006 and 2007, etc. And actually we achieved pretty high accuracy with this system, and I would, go ahead and make the claim that it is more accurate than the human classification. And in some cases, if you look at the last car in the screen there, it's damaged car, and it still can recognize the make, model, and the year. So how we do this one, we do it basically, we take the images and we extract different components from the image. So we do not make the classification at the image level. We try to identify some regions of interest, and all of this is done automatically. So I show here a couple of images. We extract few regions from each one, and then those, they will go through this deep neural network. We have our own adaptation of this multiple instance CNN. And then at the end, it will give you a confidence or what is the likelihood that it is in any of those classes. So the key to train or to build any of these learning algorithms is data. So the more complex the task, the more data that you need. And we hear a lot about deep learning now and AI. And that's one of the bottlenecks of those, is that it needs a lot of data. So when we tackled this approach, we had to collect, and we ended up with a database that has close to 300,000 images. And not only the number of images is large, the number of classes is also large. We have almost 10,000 classes, because you have to look at all models, all makes and years. And so this is kind of visualization what I have here. Every circle is proportional to how many from a certain category of cars we have. So here's an example again of output. So the first line there, it shows that we extracted and correctly classified these Audi A4 cars. And then the red boxes, it identified the regions that were the key in identifying this as the correct car make and model. So you can see usually the tail light is a very important feature, and sometimes it takes the whole image too. And within every box, I don't know if you can read the numbers, it basically tells like what's the confidence or what is the contribution of that small window. So once we built this system, we tried to do a few applications of this. And one that we got really interested in is more of a surveillance. So we know that there are several cameras within the city. So if we said, if we have access to those cameras and then watch all the cars as they go by, we can recognize the make, model, and create a database. And then later on, we can, if needed, we can retrieve that information. And the first application that we have in mind, imagine that you have an Amber Alert, and then it says, okay, we're looking for a Toyota Corolla, and we know like where it was spotted. We can look at the cameras in that path, and then we can come up with, if we can spot that in different locations, we can even identify it on a Google map or something like that. So to build that system, so the first part is what I talked about. You recognize the car make and model. Now that builds our classifier that can recognize cars. Now given, so the bottom part of the figure there, you're given a security camera, it captures the video. So we do the detection, we classify, we track the vehicle, we'll recognize the car make and model. We also identify the color and the time of the day it went by that location. And then we populate a database with all that information. So here's an example with a video that we captured using just like a smartphone. And for every car that we identify, so we do the detection. And then for every one, we keep 3 options, like what are the 3 most likely labels of that. So I'm starting on the left there. That's our most likely car make, model, and year would be a Chevrolet Malibu 2012. The next option would be also a Malibu 2011. And then the third option will be 2008. And then the red car there is Ford Fusion. So we detect all those cars as they go by, and we create a database that might look something like this. For every camera at every location, what's the entry time, the exit time, what's our choice as the top 1, top 2, and top 3, and then what is the color of that car. So I have here like a video with a very, so I'm gonna keep talking and while playing this. So here's like a GUI that we have developed. You select a video that's been recorded. We're kind of simulating certain camera at the one location. So you pick the video, and then as the cars are moving, it's doing the detection. So it detects person and cars, and then it has the label there on the top of every car with 3 choices. So you can see as the cars appear on the frame, it will detect, and then for each car, it gets like 3 options. So pretty much, I mean, like, as I said, we're getting close to 95 or higher accuracy on those. So once we detect those and we populate the database, now it becomes a query. So on the left there, you say, we're looking for a black Ford. And then it gives us like, what are the top 1 matches? So you select that. And then now it plays part of the video where a black Ford has been spotted, or it could be a Ford Taurus. So it gives all different models. And then it plays like few seconds of the video where that specific car has appeared and disappeared in that video. Okay, so that's kind of the first application. The second application is kind of more of a DoD application, and it highlights like the different sensor, multi-sensor fusion. And this is a project that I've been working on this for several years. I mean, probably from the late 90s. And we're trying to detect buried explosive objects. We started with buried landmines, and then with the adaptation of the different need. So we moved on to detecting any improvised explosive devices. So here's an illustration. So the threat, they could be anti-tank mines, they could be anti-personnel mines, which are smaller, or they could be any explosive devices. So we collect data with sensors such as ground penetrating radar, metal detector, infrared camera, hyperspectral imaging. And these are 3 of the systems that we worked on. There's the vehicle mounted. So you can see the radar here mounted on the front of the vehicle. The second system is a handheld system. It looks like your typical metal detector. So these are actually operational systems that have some of the algorithm we developed, and they've been deployed in various parts by the Department of Defense. The third one is more of a robotic one, and then it is remotely controlled, and that's still in early experiments. So the learning strategy is we collect data. This can be ground penetrating radar or a metal detector. We go through a learning process where we extract some features, build our learning algorithm, train them, and then develop fusion, multi-sensor fusion, and then decide basically if there is a threat under that location or no. So here's like this specific system, the vehicle mounted one. So it basically sends a signal into the ground, and then it reads or it captures that, and then you collect data that looks like this, 3D volume. So I'm not gonna but we're gonna do the analysis of this data and then decide if there is a threat under that location or no. So when we started looking at this, and again, this is to highlight the importance of AI and how it helps. When we started with this, we worked with a company. I would say they spent probably 99% of their effort in developing the sensor. So they came up with a sensor. It's a good sensor, but they did not invest any time in the algorithm or in the learning. So they were detecting 83% correct detection, but they were getting a lot of false alarms. Now, to visualize those numbers, imagine you have a road that has only 10 meters long and 4 meters wide, and the red dots there that are appearing they're all false alarms. So it's pretty much you move like a few feet and then you have to stop and dig and there's nothing. So all those are false alarms. And it took us a while to convince them that we could improve their system and we can use machine learning to improve the results. And that's basically what we did. So we took the data, we developed the machine learning, and then we identified the location. So how does the system work? You collect data, we try to identify a certain location of interest. We And then we go through a lot of learning and AI. And then at the end, we come up with a probability that there is a threat or no threat. So based on that AI system, after a few years, we were able to achieve 99% probability of detection with almost no false alarm, like 0.2%. And again, to visualize, this is now notes that the x-axis there is 1,000 meters, not 100 meters as before. And you travel 1 kilometer and then you have only 2 false alarms. So that is kind of, we convinced them like, yes, with AI, you can do better than just looking at the energy. And so it's better to invest in collecting data, develop learning algorithm, and build a system that will analyze the data automatically. And then in the last few years, we moved, this is the same application, but we went more into deep learning. So we built like a couple of networks to do the same thing. So again, I mean, these are different networks. But the key here is that the blue line is probably an algorithm that we spent 15 years trying to extract our own features and try to build the learning system. And then the other red and green and black are basically what we did with deep learning, because just to show that you can do a lot with deep learning, and it requires a lot more data, but it does perform better. Moving on to like another kind of related, it's automatic target detection, but using infrared images. So I don't have much to say here, but infrared images, they give you the advantage of night vision and surveillance from a longer distance. And so you have an image here on the left, and then those like 2 small white dots are targets. It goes through this deep learning, and then we were able to identify the location and classify them as target 1 and target 2. We also, as I said earlier, we try to focus on explainability. So we try to come up with like, okay, as the vehicle travels, here we have them color-coded. Red means that we can extract them with high confidence. Blue, we're extracting them with a much lower confidence. And you can, I mean, I'll play this video here, then it shows that, okay, as the vehicle moves, even though like those are, they may be like low resolution, hard to see, but they were detected and identified correctly by the algorithm. Another application, which is slightly different now, shifting more into the health domain, we developed like a system to analyze video. And what it is, so we worked with doctors that record video simulations. So they have interns, nurses in the pediatric, and they try to simulate certain emergency scenario, and then it will be recorded, and then it will be analyzed later on. So basically, so think of it this way: you have a dummy there that can simulate certain emergency, and then the physician will record this, and then after that he goes back and watches the video and try to identify if there's anything done incorrectly, and then he has to debrief the attendee. Then after recording probably hundreds of video, he realized that's very labor intensive. He cannot sit there and watch them frame by frame. And the question becomes, can we automate this? So the first thing that they were interested in was, can I identify all CPR scenes within the video? And what we did, so you take the video, and we developed an algorithm that can break that and then identify every CPR scenes, and then it will give you there, and then you can play that, so you don't have to watch the video frame by frame. So it goes, I mean, there's a sophisticated system that analyzes the video, divides it into shots, performs segmentation. It does some temporal analysis to look at to identify the CPR scenes. But it was, so let me show you how. So we developed this GUI for the physician where you take a video recording, you load that, and then you're going to see like the video is playing on the top left there. And then we're going to probably segment that and identify all scenes, all the CPR scenes, and they're going to appear below there, where at every time instant, so the green dots there, the green lines are where we have CPR scenes. And then the physician can select anyone. We also have identified if the frequency of the CPR or the timing is done correctly, and you'll be surprised how many, even though they are like experienced personnel, they either do it too fast or too slow, and then we come up with the frequency. And so that was, again, doing machine learning and training based on what we identify as a true CPR, and then the algorithm will take over after that, and it can process any video. So I'm gonna skip the rest of that. So I think I'm gonna probably, I'm gonna skip this one because, so I think I don't have much time left, so I'm gonna skip to the last part, which to emphasize like two projects that we started collaborating with Vsoft. And the first one is we're gonna extend our 3D vision tools that we've been using for, I have a PhD student who's been working on 3D vision for autonomous driving, analyzing that LiDAR data and RGB data. So we're gonna transition on and apply some of the methods that we've been developing to the Lumo Segway autonomous pod. We just received this one, and this is one of the projects that we're collaborating with Vsoft. The other one is video analysis for social distancing. This is where we take video and we're basically identifying people as they move. And the goal here is to keep track of the distance between these people. And so this is slightly different from your regular camera because this is the fisheye camera and you have a top view. So we had to adapt and use different algorithms. So I'm gonna keep this video playing while I talk. So you can see that as the video we're detecting, so those blue boxes and the numbers are how confident we are in those being people. And then the next step is, can we identify what is the distance between all those identified boxes? This is non-trivial because we're going from 2D images to 3D, and then it's going to require transforming to the 3D world coordinate system to come up with actual physical distance and not distance in pixels. So I think that's probably all the time I have. And I'm going to stop here if there are any questions.
All right, we did get 4 questions, and I'll go ahead and ask you them.
Okay.
This one was asked a little earlier. I believe it's referring to the cars example back at the beginning. Can this technology be applied to prevent crime or vandalism on campuses?
Yes, that is our initial goal. And we approached the city police, and we had a meeting and we showed them what we can do. They got really excited about this. Mm-hmm. And then they referred to their bosses. And then unfortunately, the privacy issue came up. Even though we don't use any private information because we track the license plate without recognizing the owner. But because if the police try to use this, they have access that they can map the license plate to the person driving that car. And they said that's gonna sound violation of privacy. So, but after that, we kind of approached the campus police and they gave us access to their camera. And we did look, and we were moving in that direction of just in the recognizing for the purpose of the safety, but we haven't made much progress. But yes, the short answer, it could be used.
Perfect. And that was actually someone's kind of follow-up question. Are there privacy concerns with the car solution, and how would you address those concerns?
So from our perspective, no, because we don't use any additional information that what you see on the road. I mean, we recognize it's a red Toyota car. That's all the information. We don't know who's driving that or anything like that. So yes, I mean, we don't have access to the database that maps the license plate to the person.
All right, and then this one's about the explosive detections. With explosives, what happens with even the smallest variants of false negatives? Because that seems to be a big liability.
Right, so actually that's a very good, and I'm sorry I didn't have enough time to go dig deeper. It really, so we have two different scenarios. So there is you can think of them as a wartime scenario and peacetime scenario. So peacetime scenario where you go to a certain area and the goal is to clear it. If it has any explosive devices, you're just gonna go ahead and clear that area. Time is not an issue, so you can go over it and then repeat, and the goal is to get 100% detection, and we don't care much about the false alarms, because if you have all the time and you dig and there's nothing, it's just a can of soda, then it's not a big deal. Now, the wartime scenario is different. When you're moving and then the enemy is shooting at you, you cannot stop and dig unless, so that's where you can tolerate 90% PD would be acceptable if the false alarm rate is very, very low. So it depends on the scenario.
Yeah, and then this kind of leads into the next question. Where do you see AI in the military like 5 years from now?
So the current project that we're working on is what I showed that few slides with the IR images. And the goal here is to have not completely machine. So we're trying to use AI to assist the soldier. So instead of the soldier looking at the images and then trying to detect and identify threat, so the AI will be used to detect, identify threat, and kind of sort them, and then give that sorted list to the soldier, and then the soldier is still the one that's going to make the decision, but at least you narrowed and you gave him like the 360 view and you identified the threat from all different locations.
All right, and then let's see. Will social distancing be the norm in the future, or will we go back to normal? I guess in your opinion, how would you answer that one?
In my opinion, I don't think we'll ever go to normal. I mean, we've been into this for 4 or 5 months, and the longer it's going to go, the harder it's going to be that we'll forget it. So, I mean, I don't think you're going to see much of the handshaking and the hugging in the near future.
I see that. All right, we got another one here. Could the traffic solution be utilized to monitor high volume traffic areas such as major interstate overpass and intersections during rush hour in major cities? And are there limits on how much data can be processed and analyzed per second?
So the car make and model actually is part of a lot of, I think the main area is more of intelligent transportation system. So yes, so it could be, so one of the use, for example, that I did not mention is even going through, trying to identify the traffic. So you could identify if it's, I don't know, semi-trucks or SUVs or small cars going more onto this road than another. As the limit, the detection can be done super fast. It's almost like the videos that I showed, we can do it almost real time on a regular PC. What takes time is to train the system. Now, because as I said, we're using 300,000 images. So to train the system, it might take days or even weeks. But once it is operational, it can be done like super fast.
All right, perfect. And that was our last question. So I think that is all we have for you.
All right.
Perfect. Well, thank you so much for joining us.
Oh, thanks for inviting me.
You made it just in time with a minute to spare.
Okay, good.
So thank you so much.